Angles in a circle part 2. Let's just get right at it. Let's do a little review question first. What circle property, now I know there are a lot of them, I believe up to now 7 of them. Which circle properties are we looking at here in this question? Well, first off, you have to realize here's a circle and there's a triangle. But if you look at it in more detail, you realize that this triangle or angle here is inscribed. It's on the outside circumference, and it's only taking up half the circle. So this is the semicircle rule. And if you remember, the angles in a semicircle property, the inscribed angle in the semicircle is 90 degrees. Can I just draw like a big, huge, boxy thing to show that's 90 degrees? So that's 90 degrees. Based on that, what else do we know? Well, we know that since that's the center, it doesn't always need to have the dot, but, oops, it doesn't need to have the dot there. It should have the dot there to show it's the center, or having the letter O kind of signifies it's the center. So that means this line and that line, as well as that line, those are all radii, or radiuses. And radii are all equal. That's a radius, that's a radius. So that those radii are equal to each other, which means this triangle is an isosceles triangle. And if you remember, isosceles triangles, where the two sides are equal, their two base angles are also the same. Okay, that's the isosceles triangle rule. Hopefully you know from before. So if we know that's 80, and all the angles in triangle add to 100, that's 80. That means we have 100 degrees left over. That means these two base angles have to be equal, so we split that missing 100 into 2 equal parts, which means angle 3 has to be 50, right? Because, again, that's 80, the leftover is 100, so that has to be 50, and that also has to be 50. So this should be 50 degrees. Now if we know that's 50 degrees, this is 90, that we figured out using the semicircle circle property. So that means this must be what? If the whole thing's 90, that's 50, that means this must be 40. Because this plus that gives you the full 90. So angle 4 should be 40 degrees. Now, how do we get angle 5? Well, angle 5 is comes from another radius. That's a radius, that's a radius. We have another isosceles triangle. An isosceles triangle like this one, two sides are equal, means the two bases are equal. Two ways to do this. You can realize that that's 80, and the angles in this total line have to equal 180, so that must be 100, and then 100, the two missing angles will be 80 degrees divided by 2, or you can realize that's the base angle of 40, this must also be a base angle of 40, so either way, this is 40. Alright, let's see how that works. So again, using the angles inscribed in diameter is equal to 90 degrees. That helped us get this part here. And then the other part is that property from before is that chords of equal lengths will contain central angles of equal value. We didn't really use that one in this case. They did. And again, the thing I mentioned to you that two radiuses or radii in a circle will create an isosceles triangle. And so there you go. That's what you need. This is 50 based on what I just told you from before, because the isosceles triangle rule. That's 40 because 50 take away from 90 is 40. Complementary angles, as they say. So they're complementary angles. And then the from isosceles triangle rule there. All right. Okay, let's move on. And this one they call the rabbit ears property, and it says that inscribed angles, remember inscribed angles are angles on the outside, on the circumference, having or containing or subtended by the same or equal chords or arcs have the same angles. Okay, here's what that means in English. So here's CD, that's a chord, and that would be an arc. The line is the chord. And if we have that angle there, and then we do another angle here, just for simplicity, let's call that angle F, that angle E, and let's call this angle G. What this is saying is because those three angles are all contained by or are coming from this chord, the same chord, or also the same arc, kind of go hand in hand. That means those three angles must be equal. Okay, so again, angle F, angle E, angle G, all contain the same chord, CD, and the same arc, CD, meaning those three are equal. It kind of looks like bunny ears if there were just two of them. That's why they call it the rabbit ears property. Okay, so they again have the same chord. They also have the same arc, CD, and all those angles then must be equal because they come from the same arc or chord. So this just means if the angles come from the same arc or chord, they are equal. Equal, equal, equal. All right, here's another one to look at. What if you have a situation like this, where you've got that triangle and then this triangle here, and the two chords, if they have the same length, let's say JK and MN. So JK, let's say, and MN, if they both had the same length, they're equal to each other, what does that tell you about the angles that they contain? Now again, when they say angles they contain, here's what you do. Here's a chord MN. The angle that it has, or subtends, the fancy word, is this one right here. Or you could say this angle comes from chord MN. That's just another way to sort of think of it. And then, so here's this chord, JK. What angle comes from it? Angle L. It's called the angle directly opposite from it. Okay, so what do you know about that angle and that angle? What do you think the rule is going to be? The angles will also be equal. So this angle, MPN, and KLJ are going to be equal. Now they made a typo here. This should be KLJ. And then MPN is good. So that's our next property of angles in a circle, meaning that those two angles are equal. So if the angles come from the same chord or arc, they're equal. And if those chords, they don't have to come from the same chord, but if those chords are equal, then the angles that they have, or they come that give rise to, are equal. Give rise to wasn't the right word there, but you know what I mean. Okay, let's take a look at a practice question here. So angle 1 and 2, what do we know about them? Well, first off, here is arc BC. Arc BC has in it, or subtends, these two inscribed angles, angle 30 and angle 1. And what did we just find out from before? An arc or a chord that has an inscribed angles, those two inscribed angles are equal. So if that's 30, this must also be 30 degrees. This angle, 25 and 2, also, where do they come from? Well, they're actually coming from, or they're subtended by, this arc here, AD. So AD has angle 2 and angle 25. Well, again, angles that come from the same arc are equal. So 25 is going to be equal to angle 2. So that is 25 degrees. Okay. And let's just check to see if we're right. Yeah, they're talking about there's the arc there. That means it's 30 because they both contain the arc BC. And then this one here, I guess you can think that you can draw a chord there as well. But I mean, the arcs are chords. They kind of go, they're interchangeable, I guess, when we're talking about this. And they come from the same arc or chord, so those two are equal. All right, this problem down here, a bit of a doozy. So first off, we see that this chord has in it two inscribed angles, this 47 degrees and this angle D. So even though they're not, well, they are asking for angle D, angle BDC then is 47 degrees. So we can kind of put 47 degrees there. Okay, because they come from this same chord. Boom, boom. That's the rabbit ears one. What about angle BCD? Well, BCD, if you see that this, so we're looking at BCD, we want to note that angle there. Well, look at the this chord and that chord. They don't come from the same, these chords don't come from the same place, but they are equal because those little dashy lines mean that. So that chord is equal to that chord, and this chord has this 47 degree angle. That means this equal length chord is going to have the same degree angle, also 47 degrees. Okay, equal chords give rise to equal angles. Now, the next part, to try to figure out what 15 is, there's a bunch of ways to do that. The easiest way is to realize that DA, right here, this arc DA, gives rise to two separate angles. It gives rise to this angle here, angle C, which is 15, and it also gives rise to this, again, it doesn't really give rise to the angle, but you know what I mean. It has, I guess, this angle here, so these two must be equal. It's kind of like bunny ears as well. So that's 15, so that must also be 15. So this is 47 because of the equal chord rule, and the bunny ear rule tells us this is 15. There's other ways you could figure that out, that's 15 as well, but that's the most direct one. Let's see if we're good. So 47 degrees, yes, because they both contain chord BC. BC has the 47 and that 47. And BCD is 47 degrees, that's this one here, because it comes from equal chords. Yeah, BD is equal to BC, that chord is equal to that chord. And the last one is 15 degrees because they come from arc AD. Right there and right there. Alright, moving along. Okay, this is an important one too. Actually, pretty an easy one. The inscribed angle, that means the outside angle, is half of the central angle if they contain or come from the same chord or arc. Here's what I mean. So again, the central angle, another way to think of it, the central angle is going to be twice the outside inscribed angle, and vice versa. So here is the situation that I'm talking about. So this central angle here, because it goes, the angle from the center of the circle, they're saying is 2 times this inscribed angle here. And vice versa, this is half of that. So if that's x, what's this going to be? 2 times x, that'll be 2x. Right? Okay, so here's a little problem for you to handle. Find the value of x, y, and z in this triangle here. Okay, so this is not that big a deal. There's a central angle. 88. It's coming from this chord AB, or coming from this arc AB. Like it says, inscribed angles that come from the same chord as the central angle are half. So this, which is coming from the same chord AB, must be half of 88. So that means that must be 44. This angle Y is coming from the same chord, so it must also be 44. So again, AOB is a central angle, and because we know that X and Y are both inscribed angles that come from that same chord. So X is 44 and Y is 44, like I just told you. Angle Z. How are we going to figure out angle Z? And it always comes back to isosceles triangles. Here, this red triangle is an isosceles triangle because that's a radius, that's a radius. Those two are equal. And isosceles triangles say the base angles are equal to each other. Well, how do we figure out those base angles? Well, if that's 88, then, and the whole triangle is 180, if we subtract 180 from 88 from 180, we get 92. So the leftover 92 degrees has to be split up equally between these two base angles. Well, what's half of 92? 46. That's 46. We're only interested in Z, so that has to be 46. So Z is part of an isosceles triangle. Degrees. Okay, now a little quirky little situation here. If you have, hang on a second here. If you've got a situation where this guy's going to move it around here for you. If these two radiuses move past the center of the circle, you get a weird situation. Now, notice over here. So angle B is this angle here. As it changes, so does the central angle. Okay, so let me just back up a little bit. So there's angle B, it's 63 degrees. Angle O is always double it. Right there. So 64 times 2 is that, and it keeps changing as we move the angles around. But watch what happens when they pull this and pull that, when the radiuses go past it. Now this becomes 120, and then the angle we're looking at is not this inside angle, it's the outside angle. The outer angle then becomes the central angle. Okay, so as that continues on, let's just show you what they're talking about. So again, when the angles, the radiuses move and flip the angle, flip over here, this outside angle becomes a central angle, not this. So if that is the central angle, that'll be half of it. So we look at the outside part, not the inside part. It's a little tricky one. You may come across it here or there. Okay. Let's not worry about proving that. So let's jump to the challenge, and let's do this. So angle 1 and angle 2. There's angle 1, there's angle 2. First off, I can see that angle 1 and angle 2 are coming from the same chord. They're coming from chord CD. Arc CD. So arc CD subtends, or has this central angle and that inscribed angle there. Did I just skip ahead? Okay. Also, it also has this angle here. So arc CD has this angle and that angle, and since those are both inscribed angles, angles on the outside of the circle, angle 1 must be 28 degrees. So those are inscribed angles. This is a central angle, and central angles, remember, are double the inscribed angle. That's 28. This must be double that. That's 56 degrees. So again, the reason why that's 28 is because that one's 28 and it comes from CD. This one also comes from CD, so those must be equal. And central angles are double the inscribed angles, so it's 56, like it says there. All right, next up, for this one here, We have a couple of the circle properties happening together. Chord ED in it has this 35-degree angle. Well, what else does chord ED have? It also has this angle here. So that is 35. We don't really need that though. Chord ED also has this central angle here. So that's 35, and this central angle must be double that. So that is 70. Okay, so that's 70. So angle 3 must be 70. Central angle coming from the same chord as that inscribed angle. And then the equal chords, equal angles rule. So there's a chord ED. It's equal to BD. So they have the same angle. This has this, which is again 35. This is equal length, so that means this is 35 right here. And you're thinking, well, this information doesn't really get us anywhere, because we want to figure out what this little sliver of an angle is right there, angle 4. Well, that's isosceles triangle again. Here is an isosceles triangle, this orange one. So that length is the same as that. Let me just draw the isosceles triangle. Same, same. That means the base angles are the same. If that's 70, then we have 80 minus 180 minus 70. We have 110 degrees left over. Well, that 110 degrees has to be divided equally by these two angles. So that means that this must be half of that, 55 degrees. And that's 55 degrees. Well, if we know that that entire thing is 55 degrees, and that's 35, can we figure out what that is? Yeah, it's just the difference. 55 minus 35 is 20 degrees. A little bit tricky. Hopefully you're following me on that one. Let's just take a look. So that's 70 because, again, it says their central angle is double the inscribed angle. Inscribed, double, central. And that's 20 because, if you can read that, yeah. Isosceles triangle and a few other things combined together to get that. The whole thing's 55. That's 35, so the difference is 20. There you go, and that is the end of the lesson. Talk to you later. Bye.